So I just wanted to start today by writing this on the board because the video cut out before I could write it last time. So the punchline was this, and I explained everything except that I didn't get to write what the theorem was. It was that the initial complex of a lattice ideal I with respect to a W is the regular subdivision of the cone corresponding to the ellipse W. So I just wanted to write that on the board and just write a corollary that because of the general theory of subdivisions, a corollary is that this thing is going to be homeomorphic to a sphere or a ball. And this just follows from the theory of subdivisions. So this is left over from last time, and maybe the only comment that I want to make about this is that, remember what we did last time was basically to study to follow the goal of studying a lattice ideal by going to the initial ideal and the initial complex. So last time I showed that if you wanted the initial ideal, that translated into an optimization question in integer programming. And then if you wanted the initial complex, then it translated to this question about regular subdivisions. So there's nice combinatorial descriptions of what these initial ideal and complex are. Okay. Now, what I want to do today is the following. We're studying these lattice ideals, and one thing we haven't addressed is how do we compute the things that we normally like to compute, right? Like maybe Hilbert series, which might be fine or coarse, or maybe Betti numbers, which might be graded or not graded. Okay. Or free resolutions, which again might be graded or not graded. So these are things that we like to compute. What can we say about them for lattice ideals? And I'll remind you that for monomial ideals, we had nice answers to these questions. And so basically what I want to show you today is, or begin to show you, is that, that there are also nice answers to these questions for lattice ideals. Okay? So maybe the first thing to do is talk about this column. So, well, no, I mean, let's even talk about just the question of Hilbert series, okay? And so let's talk about it in the context of this example that we have here, okay? So this is the example that we've talked about several times, the semigroup generated by 3, 0, 1, 1, 0, 2, okay? We did this and we figured out that the lattice ideal is generated by a single guy, which is this guy right here. So let me just write this out. In this example, the lattice ideal looks like this, and now we're asking ourselves, how can we find the Hilbert series of this guy? Well, if you look at this thing does not have a Hilbert series. And so So I see you guys kind of looking up surprised, like what on earth am I saying? Everything has a Hilbert series. Well, remember that back when I defined Hilbert series, we had a very important requirement, which is that the ideal needed to be homogeneous. And the thing is that you can't decide if this is of degree 5 or degree 6. Now, because we've talked about monomial ideals for the whole semester, we've never had to worry about this because the generators are just a single monomial with a well-defined degree. Okay? But this is not a homogeneous ideal, and if you're not a homogeneous ideal, you don't have a Hilbert series. Okay? So the problem is that this is not a homogeneous ideal. And so that means that we don't really have a Hilbert series unless we're careful and we do the following thing. So here's the problem, but the solution is the following. The thing is that really each one of these variables x, y, and z corresponds to each one of the generators of Q, right? And actually, we have talked about these things as some sort of weights. And so what I'm going to do is that I'm going to weight my variables according to the element they correspond to. Okay? So the solution is that it is homogeneous as long as we change the grading. Okay? So we don't want x to have degree 1, z to have degree 1, y to have degree 1. What we're going to do is say that the degree of x is going to be 3, 0. The degree of y is going to be 1, 1. And the degree of z is going to be 0, 2. Okay. So if I do it in this way, then what's the degree of x squared z cubed? Well, we have 2 of these, 6, 0, and 3 of these, 0, 6. So that means that this thing has degree 6, 6. And if I say that y has degree 1, 1, then 6 y's are going to have degree 6, 6. Okay. So if I just change, I mean, this is kind of like the multigradients that we talked about. We used to say that the degree of x was 1, 0, 0. The degree of y was 0, 1, 0. And the degree of z was 0, 0, 1. Well, now we have to do it a little bit differently and use these guys. Okay? And so that's the first proposition. If I have a my semi-group looks like this. Let's say in z to the d. Then the lattice ideal, which is an ideal in this polynomial ring, is homogeneous with respect to the grading where the degree of xi is equal to ai. Okay? And the proof is basically the same thing that I did here. I need to check that for every generator, both of these guys have the same degree. Right? So let's take a generator, xu minus x to the v. And that means that u minus v is in I sub L. Okay? So then what's the degree of x to the u? Well, x to the u is x1 to the u1, x2 to the u2, etc. And that means that the weight is, I have u1 times the weight of x1, u2 times the weight of a2, x2, and un times the weight of an. Okay? And the degree of x to the v is v1 a1 plus dot 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 plus vn an. Okay? And I have to justify that these two guys are the same degree. The way that I do that is that if I subtract them, then you're not going to see down here anymore, so let's go over here. Then the degree of x to the u minus the degree of x to the v is going to be u1 minus v1 times a1 plus etc. plus un minus vn a sub n. Okay? But the key thing is that because x to the u minus x to the v is one of the generators, right? It lives in I sub l, and that means that u minus v lives in. I wrote this wrong, right? This should have been L. But remember, what is L? L is the space of relations of the AIs, right? So if u minus v lives in L, that precisely means that u1 minus v1 times the first vector plus dot 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 plus un minus vn times the last vector should be 0. Okay? And so that means that for each one of the generators, the two pieces have the same degree. Okay? And so that means that this is a homogeneous ideal now, and now I have a way of talking about the Hilbert series, but so you have to be very careful. Whenever we talk about these Hilbert series, they have to be Hilbert series with respect to this special grading. Okay? So now I sub L is homogeneous and has a Hilbert series. With respect to this grading. Okay? So now at least we can make sense of what this means, the Hilbert series. Okay? Now, as far as the Betti numbers and the free resolutions, well, if I forget about this stuff, then these things make sense, right? A free resolution is what we know it is. We have some ideal. We want to resolve it using free modules. And then the minimal way to do that is described by the Betti numbers. Okay? And so what I want to do now is carry that out in a couple of examples so that we can see how this works. Okay? So maybe what we'll do is talk about Betti numbers of lattice ideals. Okay. And let's start with this example. So here's our ideal, okay? And we want to resolve it. So remember, what do we do? Well, the first step is that we take each one of the generators of our ideal. In this case, there's only one of them. And then map R to the number of generators into I sub L by saying that the first generator here mapped to the first generator here, the second generator to the second generator, etc. So here I'm just saying how many generators does I sub L have. And it has one generator. Now, in the next step, I have to say what are the syzygies between the generators. What are the syzygies between this one generator? Well, if you only have one generator, you don't have syzygies, right? The syzygies are meant to be relations between some of these guys, and if you have just this guy, there's no relations. So that means that already we're done. Now, remember that we actually had a way of writing this. We would write the map here saying take the first generator into x squared z cubed minus y to the sixth. Okay? Now, what is the reason for doing this? The thing is that actually, I can also think of this as having a grading. Okay? Because in the way that we saw in that board over there, we can think that x squared z cubed minus y to the sixth is homogeneous of degree 6, 6 in here with respect to that funny grading. Okay? And so I can make this also a graded map by putting a degree shift here. And so that's what I'm going to do. I'm just going to put the degree shift 6, 6. Okay? Where you have to remember that we're doing it with respect to those weights of the variables. And so this right here is the graded free resolution of I sub L, and it's minimal because how could it be shorter than this, right? You need to generate the ideal, and there were no relations. Okay? So this is it, and that means that we have the Betti numbers. What are the Betti numbers? Well, there's only one non-trivial Betti number, which tells me that there's a summand here. So the Betti numbers are that in degree 0, I have one thing. So in step 0, I have one generator of degree 6, 6, and all the other ones are 0. Okay. Okay, so that's kind of a silly example, right? There wasn't a lot happening here, and probably we're not going to be able to generalize anything just based on this example. How do we build a more interesting example? Well, what we need is a more interesting ideal. And so if we want a more interesting ideal, we probably need more generators that have more relations between them. And so let's talk about an example that we liked last time, which is the example of coins. So maybe this will be example 1. And we'll have here example 2. And in example 2, Q is the semigroup generated by 1, 5, 10, and 25. And then we had a lattice ideal that basically told us that 1 penny is equal to, 5 pennies are 1 nickel, 2 nickels are 1 dime, and 2 dimes and a nickel are a quarter. Okay? So let's try to figure out what the free resolution of this thing is. Okay? Well, now this is going to be a more interesting example. We can get started, right? So we can say, okay, well, at least I know what the first step is, right? Because I sub L is given to me as 3 generators. And so the first step is going to tell me take 3 copies of the ring and map them so that the first generator maps to this guy, the second generator maps to this guy, third generator maps to this guy. Okay? And let's go ahead and include the shifting. Okay, so what's the shifting here? Well, I basically have to say what are the degrees of these guys. Just like the degree there was 6, 6, what is the degree here? Again, we have the issue that in our old version of degree, these things are not homogeneous. But in our new version of degree, what are we saying? We're saying that the degree of a penny is 1, the degree of a nickel is 5, the degree of a dime is 10, and the degree of a quarter is 25. Okay? And according to that grading now, this has degree 5 and this has degree 5. Okay? So I get a 5 here. Then this has degree 10, this has degree 10. So I get a 10 here. And then these guys have degree 25. Okay. So what do we do next? Well, we need to write the syzygies, right? And I know you don't want me to do this by hand on the last day of class, right? We're done with this. So what you do is, really the way you do this, you just feed it to a computer. Okay? So at least I wanted to get started so that we remember how this works, but really, I hope you've learned this lesson that these things are better left to a computer. So you do it, and the computer tells you this. It tells you this, and then the shifts are going to look like this. 15, 30, 35, 40. Okay. And this is the minimal free resolution. So this is done by computer. Okay. Okay. So what does that mean? That means that we have the Betti numbers. What are they? Well, in the first step, we have a 1 in degrees 5, 10, and 25. Here, in step 1, we have it in degree 15, 30, and 35. In step 2, we have it in degree 40, and otherwise, it's a 0. So these Betti numbers are the summary of this free resolution. Okay. So are you guys remembering how these things work? We haven't talked about them in a while. Any questions about it? Okay, now let's see. So we have this in these concrete examples, but remember that when we did this for monomial ideals, we had this very nice theorem. So for monomial ideals, we had this theorem that told us that if you wanted to compute the Betti number of a monomial ideal, we had a topological way of doing it, and this was using that, I forget if it was the lower or the upper Koszul complex. So we said that basically there was a way of interpreting this. I wish that actually, can someone look in their notes and read this off to me so I get it right? So I think it was something like this. Where this was called the lower Koszul complex. And this was a wonderful theorem because basically it told us that we don't have to feed these things to a computer. We don't have to do them algebraically. If we manage to get a good description of the lower Koszul complex, then we just compute the homology of that thing, and we get our Betti numbers. Okay. Did anybody find it? Is this right? Oh, yeah. Yeah. I think I'm getting ahead of myself, as you can see. It's a KB, and it's upper Koszul complex. And this is our dictionary between algebra and topology / combinatorics. Okay? And so what I want to do now is the same thing for lattice ideals. I want to show you that we can also compute the Betti numbers of a lattice ideal in the following way by just computing the homology of something. That something is denoted delta sub b. So now you see why I made that mistake. Okay. And I need to tell you what this is. Now, think about it. How do you prove a theorem like this? Well, the thing is that we already have a theorem like this, and we have a proof for it. And remember that this proof was a little bit intricate. We had to use these Tor functors, but we could do it. So now, if you want a theorem like this, then basically what you do is that you run the same proof and see what comes out of it. And so maybe what I'll just tell you right now is that the proof of this thing is analogous to the proof of this one. Analogous to the one for monomial ideals. That's how you discover a theorem like this, and then you can state it nicely as follows. Okay? So I need to tell you what this delta sub b is, and it's actually fairly simple. Delta sub b is the following thing. It's the collection of subsets of 1 up to n, such that if you start with b, and you subtract the generators corresponding to those guys, then you are still in Q. Okay. So maybe what we should do is an example of this so that we can see how to parse this stuff. Okay. So example. Let's try to explain this Betti number right here. Okay. So in example 2, Betti 1, 35 is supposed to be the dimension. So I switched. I've always used F in this class. I don't know if you guys have gotten annoyed that the book always uses K and I always use F. But I started with F and I didn't want to change. So according to this should be the dimension of the first homology of delta sub 35. Okay? So what is delta sub 35? Delta sub 35 is the collection of subsets from 1 up to 4, such that if I take 35 and I subtract the generators in my subset, I'm still in Q. Okay. So let's draw delta 35. Well, the elements are 1, 2, 3, and 4. But actually, it's going to be more convenient to think of them as being 1, 5, 10, and 25. let me draw it like this. Draw it like this because I know what's going to come out. 1, 10, 25, and 5. Okay. Now you should notice that already here I'm claiming that these guys are faces of my complex. What does that mean that this guy is a face? It means that when you subtract 25 from 35, you are in Q. 35 minus 25 is 10. What's Q? Well, Q is, I mean, this is kind of a fancy way of saying the natural numbers, right? Because any natural number can be, you can make any integer amount of cents using these coins, right? So Q is just the natural numbers. Okay. So 35 minus 25 is a natural number, 35 minus 10 also. Well, remember that 0 is a natural number. It's very important. Okay, so should I put the edge between 1 and 5? Well, I put it if when I subtract 1 and I subtract 5, I'm in Q. And that's true. Or if I subtract 1 and 25 from 35, I'm still a natural number. If I subtract 1 and 10, I'm still a natural number. If I subtract 10 and 5, I'm a natural number. If I subtract 25 and 5, I'm a natural number. But you see, this is why it's very important that 0 is a natural number. If I subtract 25 and 10, I get 0, which is a natural number. So those are the edges. Now let's see what triangles I need to fill in. So for example, triangle 1, 5, 10. I should fill in because I can subtract 1, 5, and 10, and I still land in Q. Okay. I can also subtract 25, 5, and 1 from 35, and I get 4, so that's a natural number, so this guy is also in my simplicial complex. What about this phase? Well, this is the first phase that I'm not supposed to put in, because if I subtract from 35 the numbers 25, 10, and 1, I get negative 1, so I fall out of Q. So I don't put that guy in. And if I subtract 25, 10, and 5, then I don't put that guy either. And so there's no more triangles. And then I look for tetrahedra, but if I subtract all 4 guys, I also am not a natural number. Okay? So this is delta 35. And, well, that's good because this Betti number is 1, so that means that I should expect to see a one-dimensional hole here, which I do. Now, how do I cover up this hole? For example, if I look at delta 36, then what that does is that now all of a sudden you are allowed to subtract 25, 10, and 1. Okay. And so what you get is these 3 guys. You don't get the back face, and this thing has no holes, which means that you should never see 36 anywhere here. Okay. What about delta sub 40? What do you get? Well, the thing is that you can subtract any 3 of these guys, but you cannot subtract all 4 of them, right? Because the sum of the 4 of them is 41. And so what you get is a hollow tetrahedron. And that, again, is very good news because we should expect to have a 2-dimensional hole, and that's exactly a hollow tetrahedron. Okay. This is cool. I like this. You can kind of see it before your eyes. Okay. So that explains this guy. Okay. Maybe we should explain one of the 0-dimensional guys. So what about delta sub 10? How does that look? Delta sub 10 looks like this. 1, 5, 10 and 25 doesn't appear. And this right here is a zero-dimensional hole. So that explains this guy. Okay, so that I hope makes you believe this theorem. At least believe that it's a plausible theorem. And maybe it's good if we do it here also, okay? So that we see how this works. So how do I get to explain this Betti number? Well, what I should do is compute the simplicial complex delta associated to 6, 6. Okay? So where's 6, 6? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so this guy right here is 6, 6. Okay. Now, what are the things that I need to try to subtract now? The generators, right? I need to figure out, can I subtract 3, 0? Can I subtract 1, 1? All of these things. Okay? So for example, can I subtract 3, 0? If I subtract 6, 6 minus 3, 0, I get something in Q. So I should put 3, 0. Should I put 0, 2? Well, I should put it because if I subtract 0, 2 from 6, 6, I am in Q. Okay? And if I subtract 1, 1 from 6, 6, I am in Q. So all the 3 vertices get to stay. Now let's look at the edges. Should I put in this edge? Well, I try to subtract 3, 0 and then 1, 1. And I fell out of Q. Okay? So you see it gets more subtle because their Q was very simple. Here Q is more complicated. Okay? Here I cannot subtract 3, 0, 1, 1 because I get a hole here. So that means that actually this edge doesn't go in the simplicial complex. Okay? What about this edge? Well, I subtract 3, 0, 0, 2, and that's in Q. So I put it in. Now what about this guy? I subtract 0, 2, then 1, 1, and I fell out. So this hole means that I shouldn't put this guy in here. Okay. What about the triangle? Well, there's 2 reasons why I shouldn't put it in. The first reason is that if I subtract 3, 0, 0, 2, 1, 1, that is a hole. So I shouldn't put it in. The second reason I shouldn't put it in is that I'm claiming that this is a simplicial complex. I haven't proved it to you, but if you believe that it's a simplicial complex, then you can't have the triangle because you would have to have these edges also. So in either one of those 2 ways, you see that this is delta 6, 6. It has a zero-dimensional hole, and so you get a 1. But by the way, so let me show you. So these were the 3 holes, and then what were the non-holes? This one, and this one, and this one, and this one. So basically what this guy looks like basically depends on what this little thing that I hope you can see has kind of the shape of a cube. Basically, you just have to see where that cube lands with respect to Q. What points are in Q, what points are not in Q. And that's what determines what you get to put in the simplicial complex. If you happen to know the word zonotope by any chance, then the correct word is zonotope, not cube. A zonotope is a projection of a cube into a smaller dimension. So it looks like a cube, but really it's not a cube because it lives in 2 dimensions. But so it's kind of subtle, because it turns out that this is the only bad point that causes holes. And actually, I wouldn't have predicted that. And I don't see at all what's special about this 0.6, 6 in this semigroup Q. But it turns out that this is the only place where you can put your zonotope and have it land wrong. If you put it anywhere else, then you're going to have some points in, some points out, but the point is that you don't get any homology. So that's the kind of combinatorics that ends up coming into play here. Okay. Any questions about that? Okay. Maybe I'll just state it and I'll leave it to you as an exercise. It's an easy exercise to prove that this actually is a simplicial complex. If you just sit down and see what these things mean, then you'll see that this is not very hard to prove. And that means that we can take its homology and this statement actually makes sense. Okay. All right. So the thing is that now I wish that I hadn't erased what I wrote here, because our goal was basically to compute Hilbert series, Betti numbers, free resolutions. And this is basically the nicest general answer for Betti numbers. What we have here is an explicit combinatorial topological description of the Betti numbers. And as you know, if you have the Betti numbers, you can get the Hilbert series. Right? Because if you have the Betti numbers, that means that you know what the minimal resolution looks like, and you can write the Hilbert series. Okay? So from this, we get the Hilbert series. Where here is with respect to the grading where xi has degree ai. How is that? Well, again, remember that the point is that if you have a free resolution, then the Hilbert series of this guy is the Hilbert series of this one minus the Hilbert series of this one plus the Hilbert series of this one. And so all we need to know is how to compute the Hilbert series of R. And what's the Hilbert series of R? Well, it turns out that that's a little bit tricky now, because, for example, here, what's R? R is the polynomials in P, N, D, and Q. Okay? And it used to be that the Hilbert series of this thing was 1 over 1 minus x to the fourth. But we changed the rules now, and now we're giving different weights to the different variables. Now, whenever you have a P that's worth 1 over 1 minus x, I mean, every P is worth x, but now every N is worth 5 x's. And that means that actually you have to introduce that into the picture here, because that's the grading we're using. Every D is worth 10 x's, and every Q is worth 25 x's. Because of this funny grading. But that's all there is to it. I mean, in general, if the degree of xi is ai, then what you would have here is x to the a1, x to the a2, x to the a3, up to x to the an. Okay? And that means that we can write out the Hilbert series of I sub L. What is it? It's the sum of these three guys. And remember, because of the shift in degrees, we get x to the 5 over this big thing. Let's give this big thing a name. Let's call this d for denominator. So we get x to the 5th over d plus x to the 10th over d plus x to the 15th over d. 15th? 25. X to the 25 over d minus x to the 15 over d minus x to the 30 over d minus x to the 35 over d plus x to the 40 over d. That's what we get. Okay. Now, and so that's the answer. That's how you compute the Hilbert series of a lattice ideal. Once you have this thing, you just need to plug in the Betti numbers in here. Now, I want to show you something, which is that actually, I mean, what is the Hilbert series of R mod IL then? Well, we know that this is the Hilbert series of R minus the Hilbert series of IL. Right? So this is 1 over D minus all this stuff. And now what's 1 minus x to the 5th minus x to the 10 minus x to the 25 plus x to the 15 plus x to the 30 plus x to the 35 minus x to the 40? Would be a mean exercise for one of your algebra students. These factors, it's 1 minus x to the 5th, 1 minus x to the 10th, 1 minus x to the 25 over d. So what you get is 1 over 1 minus x. Okay. Maybe that's a little bit strange, but that's what it is. The Hilbert series of R mod IL is 1 over 1 minus x, which is 1 plus x squared, etc. Now, why is this not surprising? Because remember that we proved, we had this theorem that R mod IL was isomorphic to this semi-group ring, f of q. Okay? And so what I should see here are basically the things in Q. And what is Q in this case? Q is all the natural numbers. So this is the answer that I should expect to get. So in general, the Hilbert series of R mod IL is the sum over the points in Q of x to the q. Okay. This follows from this theorem. And so basically that means that by computing this Hilbert series, what you're doing is also summing everything in a semigroup. And so these are two equivalent problems, and it's hard to say. Sometimes this will be easier, like in this case. Right? This all seems like a waste of time when you see that all you were doing was adding this geometric series. But sometimes this is easier, actually. And the point is that they're equivalent problems. Finding the Hilbert series of the lattice ideal, or adding up everything in your semigroup. So that's for Hilbert series. Okay. And so that tells you, again, a very nice story of how to compute Hilbert series of lattice ideals. And then what I won't have time to tell you is that there's also a very nice story of how you actually compute the free resolutions themselves. How do you write out the maps? Okay. But the conclusion is that, as with monomial ideals, there are nice combinatorial topological ways of computing the algebraic invariance, the algebraic quantities of your semigroup, or either the ideal or the semigroup or whatever you want. And I even managed to say that before the RX voice came in.